Hello again, welcome back. Okay, then let's continue seeing how a publish subscriber middleware and communication works. Would like to remember you, we are using Rhodos as an example, but it doesn't mean what we are looking at is only for Rhodos. What we are looking at for publish subscriber middleware is very common. It's a very generic principle which is used in many other modern middlewares. For example, ROS 1, ROS 2, and DDS, and many modern middlewares use this principle of publish subscriber communication. So, I am using Rhodos as an example because I know it very well, but it doesn't mean this is only for Rhodos. This is a very generic principle. Okay, then let's continue what we were looking at. Just a second, please. This was the last thing we were looking at. We were looking, okay, we have topics and we have publisher who distributes new information to topics, and topics might have 0, 1, or many subscribers. And each subscriber will get a copy of each message which is published by any application. But now let's see how it shall work inside of the application. Now we have to see the interaction between applications and communication and topics. Okay, let's take a look. It works like this. Do you remember, this is the diagram we were using to see how the scheduling works when applications will be suspended and applications will be reactivated. And on the top of this, I am just adding the topics from the middleware. But please be aware here, this line, that is the timeline, beginning from 0, going until end of time. This line is not the timeline. These are just the different topics, like in the same way like we use here. Okay, and it works like this. We have many threads, and one of these threads might initiate an application, a communication. This is something very important. The communication shall be initiated by an active object. If the active object are, for example, threads or interrupt service routines. Okay, let's assume a thread. The thread which is going to initiate the communication, of course, has to be running. It's an active thread. Okay, this thread was working, it was suspended, it was resumed, maybe by another thread, and then it continues, and at this point it communicates. Then it calls one of its topic, the function publish, and each topic has a list of all subscribers. Then for each subscriber, we have a function which shall be called every time a message arrives. This can be a generic function, for example, put data, or activate, or something like this. It doesn't matter. It can be different from middleware to middleware. But let's assume we have a generic function which is called put data. Okay, then this publish will go through the list of all subscribers, and for each of these will call the local function put data. Then as parameter it will give the data which was published here. The application will do something, not the application, the subscriber will do something, and then it will conclude. And again will do something and it will conclude. Then this thread might continue working. Okay, here we have another example. This time thread C initiates a communication, goes through this topic calls the subscribers conclude, and then the thread might continue working. And a special case is a communication from interrupt servers. This is something very interesting. Normally, you have different interrupts in a CPU, and then you have to add something like an interrupt service routine, interrupt service function attached to each interrupt. Then every time an interrupt arrives, then this function will be called, and it's something somehow complex. Every CPU has a different mechanisms, but you have something like an interrupt vectors. And these interrupt vectors are pointers to the different functions which are going to handle the different interrupts. And that's a very special thing which can be from processor to processor different. It's not generic. We would like to do this in a generic way. Then the interrupt will not call a normal interrupt service function, but for every interrupt, it will publish the signal using the middleware. So when an interrupt arrives, the very simple interrupt service function will use the corresponding topic and send a signal, publish signal from interrupt. And then for each of these topics, we can add subscribers exactly in the same way like this. And this subscriber will be called every time and the corresponding interrupt, hardware interrupt arrives. Then the subscriber can do something, and we recommend, because it's in the context of an interrupt, this function shall be really, really fast. It shall be really, really short. Okay, it shall do very few actions, and if there is something more to do, then it can reactivate another thread. For example, execute a resume and say to this thread, here there is data from an interrupt, please handle the rest. Okay, here in this interrupt service topic, we will just do minimalistic actions, and someone else and thread will be activated and it will do the rest. For example, complex functions. And this is in this case this thread A again. And if we want, this thread can call another topics and distribute more data. Okay, this is the interaction between topics for communication, threads, scheduler in the operating system, subscribers, and event servers, which react to interrupts. Here, all these things work together. Now there is something very special. This here is very generic. It is not only for RODOS, as I said before, it's exactly the same in ROS, ROS2, and DDS. But here we have something special. We want to use the same communication mechanisms to communicate between applications and devices. So we don't want to have such things like device drivers with special interfaces. We just have a converter for topics, for the middleware, to the interface to the device. And this is the substitution of the device driver. So when we want to send data to a device, we don't call the device driver. We use publish data in one topic, which is attached to this device. And this device will get this data. Of course, we have this device manager, which is something like a driver. And when device produces data, it will call this device manager. It will do some conversion of data, and then it will publish this in a topic, like any other application. So the interaction between hardware and software shall be transparent. We don't want to have to make a difference. I am talking to a hardware device or I am talking to another application. And something very special is we can do the same if we have programmable hardware. For example, FPGA. Nowadays, many processors, many embedded controllers have an FPGA, programmable hardware, and this is done to execute very fast, very complex functions. And this is something new, what we can do. The communication between this FPGA fabric and the applications can be done exactly like the same way. We have publisher, for example, for applications, and the subscriber may be another application, a hardware device, or FPGA code. Exactly the same. The publisher may be an application, device, or FPGA code, and it will be forwarded like any other data from any other software application. Okay, and now let's go outside of the node. Up to now, everything was local in one node, but now we want the communication between different nodes. Just a second, please. Okay, to go out of a node, we need a software function which is called the middleware. And the middleware is the interface between the node or one computer to an external network. And for this communication, we can use many different hardware protocols. For example, we can use UART, SPI, Ethernet, E2C, CAN bus, and many others, SpaceWire, and so on. So we have to have a different link interface for each of these protocols. Okay, then what we have is, we have our normal communication inside of the node, then we have this gateway. And this gateway is hidden to all topics. And normally, a topic has a list of subscribers, but the gateway will get all data from all topics. Inside, it has enough information to take the decision if this topic shall be forwarded to other external node, or not, if it is a local topic or not. There are different ways making this, and this is not special in Rhodos. It can be the same in many other middlewares. For example, each gateway can have a list of the local topics, collect this list of local topics, and forward to other gateways and say, these are the topics which I have locally. If there is a message to one of these topics, please forward it to me. Another way is, for each topic, the programmer might say, this topic is only local, it shall not be forward, or this topic shall be broadcasted to all other nodes because I don't know who else requires this data. And another way is we have a list, the programmer has a list which application requires which topic and where is each application running, and then it can configure each gateway, which topics to forward, which is not. Okay, we are going from the most generic to most specialized case. The most generic and the best is each gateway looks the list of local topics and publish this list to all other gateways. So all other gateways will get continuously such list and then take the decision if someone else requires the data which he has now here. Okay, then here in turn we have a local protocol. This is a software protocol, how to distribute the message. Most of the time is using shared memory and passing pointers. And here we have an external protocol. So the function of the gateway is to convert between this internal protocol to the external protocol. And what it has to do something like a message framing. Some kind, for each of these links, we have a different type of message framing. We say when the beginning of the message is and how to recognize the end of the message. Or maybe the length of the message, only the beginning of the message and the length. But this is very dangerous because if something goes wrong, then it will be very difficult until we raster it again in the next beginning of message. Okay, in any case, we have a framing. The next thing we have to do is inside of this framing, we have to have a format, how to forward. For example, we have to say which topic we are sending, what time is it, which node is sending, and I don't know which other information for routing in this network. And then we forward using this hardware link. Then we have something like a network. This network can be something like a switch, for example, an Ethernet switch or a SpaceWire switch or something similar, or something like a bus. If we have CAN, it's only one bus, one line, and then we have broadcast distribution of messages. Okay, in any case, this message will be forwarded to other gateways, and this gateway will do the opposite from the sender. It gets a frame, begin and end of message, remove the frame, take the data, convert to the local protocol which we are using here, and distribute locally exactly like any other publisher. Okay, and then we have networks of networks. Maybe we have only one system which looks like this, or we have a bigger system which interconnects more than one switch. Then we have a gateway going from one network to the other network. And this gateway is the interface from switch to switch. And something special which I mentioned before, up to now, this is very normal case for all other middlewares, for example, ROS. What we have special is we can attach hardware devices directly to this protocol, and we have here an adapter to be able to communicate from any of these applications going through the network to any of these devices. So we don't have to know where to which link the device is attached. Okay, and something which we have to do always, we have to have a protocol conversion inside of the router. This is not software anymore. Now we are talking about hardware. It doesn't matter which protocol we use. On the software side, we have this. We have an application. We publish. We have a gateway which converts a physical link, which converts the message to this physical link, and then it sends to the physical network, to the hardware network. Inside of the physical network, we have to convert to some kind of protocol. For example, a bus protocol or a switch protocol. Then we distribute the messages inside of the switch, inside of this device. Inside of this topic, we can have, of course, much more than one port, and then we convert again to this physical link. This physical link, maybe one of these. UART, SPI, CAN, Ethernet, E2C, it doesn't matter. Okay, so we convert from this physical link to an internal protocol inside of the router, and then again to another physical link. Typically, these two links are the same, but it doesn't have to be. Maybe we have some computers which have some kind of link interface, and other computers with other kind of link interface. And then this router, this switch, shall convert from this protocol to the internal protocol, and again to other protocol going again to the next computing node. And the next computing node will look like this. Inside, we have the physical link, a UART, for example. Then we have the software gateway, which takes the content of the message. Then it distributes in the middleware, like a publish, and then we go to the application. Okay. And now, this was already mentioned, nothing new. I would like to say something about the internal structure of a switch, a typical publish subscriber switch. This is a new type of switches. We have older switches, for example, Ethernet, which forward from one port to other port. But nowadays, when more and more publish subscriber middlewares are coming, another type of network is arriving, and this is multicast. One sender and many receivers. And it works like this. This is a multicast switch, especially designed for publish subscriber middlewares. I am not talking about routers, now I am talking about switches, which is very generic. Okay, inside of a switch, hardware switch, we have a protocol converter. Here we have something like Ethernet, CAN, or who knows what. And then we have a internal in the switch, something like a gateway. And then we have different communications topics, different communication channels. These are software channels. Actually, we have only one hardware channel. That is, for example, one bus. This is a logical view of the communication. But the physical view is we have one wire, and this data will be distributed in this wire. Okay, then we have this converter from this external protocol to the switch to the internal bus of the switch. And then we can forward data from here to any other port of the switch. Something very important is this internal bus shall be much more faster than this. Else we will have a bottleneck. If it has the same speed like one of these, then only one communication link can be at the same time, and all others have to wait. And this will be a bottleneck. So what we need is a very fast communication link, and this is not very difficult because it's inside of the switch, inside of the chip, and inside of the chip we can have much more higher speeds than going through these standard communication links. For example, you are with maybe 1 megabit per second. Here inside we can have gigabits per second inside of the chip. Okay, how it works? Because we need here a higher speed, we cannot take byte for byte as they are arriving and sending in the switch, in the bus. So we will break the bus or stop the bus to the lowest speed of the communication. What we shall do is, when data is arriving, we collect all data from a complete message. And when the message is complete, first then we request the internal bus of the switch, and then we take this message, which is already stored inside of the switch, with the highest possible speed of this local bus. And then all subscribers, all other ports, will get this data with the highest speed and write internally in an internal FIFO or internal buffer. And then after, when the message is complete here, then we begin transmitting this data using the external link, which may be very slow link. For example, a few kilobits or 1 megabit per second. Don't forget, here we have 1 megabit per second. Here we have maybe 1 gigabit per second. This is 1,000 times faster. Therefore, we have to store. When the message is ready, we request, we transmit very fast, we store again, and we continue sending. And so we can have many of these communications running almost at the same time. So we store forward very fast, and then we send it very slow using another topic. In this time, another one may be transmitting another message in this bus, in this local bus. Okay. And now, another very common way of communication or way of implementation of complex systems is using hypervisors. Do you remember at the beginning, I told you, now there is a tendency, instead of having many small, very simple processors, if possible, we try to have a powerful computer, and inside of this powerful computer, we simulate many simple processors. And this is what we call a hypervisor. A hypervisor on the top of a very powerful hardware, we can simulate many virtual machines. Each virtual machine may have its own operating system and its own set of operations. For each of these, looks like it has a small, simple processor. But we have a very fast processor, and we are distributing the time. A time slice here, a time slice here, a time slice here. We have here a very big memory, and we are distributed a little bit memory here, a little bit memory here. So we get the impression we have maybe 10 very simple processors actually running in one single powerful computer. Okay, if we have something like this, then we don't need this kind of communication network. Just a second. This kind of communication network, because all of these are virtual machines running on the same computer, and if they are running on the same computer, they have a shared memory, and then we can use the memory of the host computer to transfer data from one virtual machine to other virtual machine. And it works like this. Okay, we have exactly the same like before. We have the application, we have the topics from the middleware, and we have the gateway. But this gateway doesn't transfer the messages to a UART protocol or a SPI protocol. It grows in a requested shared memory. So from the computer, we can request shared memory to put the data which we are going to send to other computers. Then the hypervisor will suspend this virtual machine. It will take a look for all messages which are waiting here. For each message, it will know which other virtual computer is waiting for this, and then it's going to copy from this shared memory to the shared memory of the other virtual machine. Okay, and then we distribute all messages which are waiting here to all other virtual machines. Then the next virtual machine will be activated. Okay, then the next virtual machine, the gateway, will read all these messages, maybe something like a FIFO, distribute, continue working. If there are some other messages to send, they will be written here in this shared memory. And when this virtual machine is suspended, we do exactly the same. The hypervisor will take the messages from this area and distribute to the other areas of other virtual machines which are waiting for this message. And this is the difference if we are using a hypervisor with shared memory, or if we are using real. Just a second. Here, if we are using real embedded controller and a network. Okay, but for the communication here, inside, on the top of the middleware, there is no difference. There is no difference if the other applications are running in the same computer node, or going through a network, or on a virtual machine, something like a hypervisor. Okay. Now, how to build complex applications. Now we have already the basics about this publish subscriber middleware, over these middlewares, over this scheduling operating system, and on the top of this we have a complex system which shall be implemented. Nowadays, what is recommended is to use something like building blocks. And building blocks is somehow different than a former way how to program. You have many functions, and the functions are called from a main program and they work together. This was yesterday. Nowadays, we try to have building blocks which are totally independent from each other. And the only way how they communicate is using some kind of middleware. it's something like this. Maybe you know Lego. Using Lego, very simple building blocks, you can build very complex, very nice toys. Okay, then this building block will look something like this. This is a software building block. From outside is a black box. The black box has some subscriber, some services which it need to be executed. Inside will occur something in magic, and then you have outgoing services, publish topics which shall be published. Okay, this is all what you need to interconnect many building blocks. But that's not enough. You need an interaction between the building blocks and the underlying operating system. And this is how to request some local resources, for example, request time, when to be executed, request memory, or interrupt services or something like this. Okay, this is the interaction to the operating system. But for the interaction between applications, we shall not take a look to this. We have only the interconnection from topics to go from one application to another application. One application is providing services, and other applications are going to use these services to produce something more complex. Okay, inside of the application, I said before, it shall be a black box. From outside, you don't know what is running inside. But inside you may have one thread or many threads, or many interrupt service functions, or many subscribers, and many publishers, and event servers, and something like this. But for you, it doesn't matter. You see only this interface, how to interconnect applications with each other. And then we built a network of applications. So, looking at the hardware, you build a network of hardware nodes, so you interconnect the nodes, and this is the hardware. And from the software side, you make something similar. You have these building blocks, and you interconnect these building blocks using the middleware and the communication. And something very special, this network of applications may be distributed among all hardware nodes. So it's not a local thing for a local computer. This distribution, this network was in the world control system. So these two may be running on this computer on this side, and this may be running in another computer on the other side, and so on. And on the bottom, we have the local operating systems. Okay. And then we have different nodes. I said before, we have a network of applications, and for the applications, there is no difference where the other partner is running. So we have to have gateways, like before, and this gateway will take messages for any building block forward through the network, or maybe share memory if we are using virtual machines, and a hypervisor come to the other gateway, and this will be distributed to the local applications in the other node. Okay, and now let me show you some examples how to build complex applications using very simple building blocks, and how to expand. That is something very important, how to extend the global application without having to modify the building blocks. So you have created a building block, and you don't need to modify it to build more complex applications. Let's say a very simple device. You have an input device. This input device communicates using this middleware. Do you remember how we do it? To a controller. The controller gets data from this input device, computes something, and publish the data to the output device. And then we are controlling here maybe a closed loop control, maybe speed control or something like this. We are getting the speed, computing how much gas we have to give to keep a constant speed, and then we control the device. And now we want to extend this. We want to add a monitor to be able to see what the controller is doing. So we use another building block. We don't need to change the controller. Here we are talking only to the output device. Here the monitor is hearing everything which the controller is doing, something like a black box or something like a flight recorder. So if something goes wrong, we can take the monitor, see the content of its memory, and then we can reconstruct what was the problem and try to debug and correct the problem. And the nice thing is you don't need to change the controller. It's exactly the same controller like here, like here. You are adding just another building block, add a subscriber to this middleware, and the messages from the controller will be published, forwarded to both, to the output device like here, and to the monitor like here. And now, a little bit more complex. We would like to add fault tolerance, redundancy. So we take exactly the same controller like here. We don't need to modify it. We replicate the controller 3 times in this case. And maybe these 3 times are running on different hardware. We don't care if they are in the same computer or they are in different computers. For us, it's exactly the same. So we have the input device. The middleware will distribute its data, which is published to all subscribers, so to these 3 controllers. Each controller will compute exactly the same like here and just publish. Who cares who is going to use the data? In this case, the output device. In this case, the output device and the monitor. And in this case, something else. We have a voter. This voter has the same interface like the device, so the controller they don't know if they are talking to a voter, a software application, or talking to the hardware device. Sorry. Okay, the voter will collect all these control signals from all controllers and compare and take the decision what is probably the right decisions, and then forward to the output device. Maybe if 2 says to the left and 1 says to the right, then the voter will say, okay, the majority says to the left, so let's go to the left. Or maybe it builds the average of all signals, who knows, it doesn't matter. But for the controller, we have exactly the same controller from the very simple system. And now we have maybe a problem. We have here a single point of global failure. If the computer where the voter is running fails, then the system is going to fail. It doesn't matter if we have replicated 3 times the controller. Here, the communication will be broken, the output device will get nothing, and then the system breaks. Okay, we can change this. We can add another voter. We don't need to change this application of the voter, just initiate another voter in another computer. And exactly the same like here, all voters, maybe 1, maybe 2, maybe 3, it doesn't matter, will get a copy of all these messages distributed by the middleware. And we don't care in which computer they are running. One voter is forwarding data to the output device, and the other voter is just waiting. As long as this voter is producing data, it does nothing. It can be hearing the data from the other voter, and if it realizes it's not working anymore, then it takes control and then it forwards its data to the output device. So we have implemented fault tolerance on the controller, on the voter, and so on, without having to change a single line of code of these building blocks. They are exactly the same, exactly the same like the very simple application like here. Okay, and now let's take a look here inside of the middleware. Now let's talk about topics. How can it work? Okay, we have the input device, for example, the joystick from the pilot or the side stick, and it publishes its data in this topic. The controller gets this data from the input device, makes some computation, and forward the result to the output device. Maybe these slabs. Okay, and this, for example, an aileron from an aeroplane, for example. So we compute maybe which angle shall we have according to the position of the joystick and the speed of the aeroplane, and then we forward this. And then we want to extend this. This is a very simple process. No redundancy. Okay, now the next step will be to add the black box, the flight recorder, or maybe a light box. Here we don't change anything. It is exactly the same. We add only this monitor, which is here into these both topics, what the pilot is commanding and what the controller is doing. And it is only writing and writing and writing. If something was wrong, then we can look inside and find what was the problem. Okay, so exactly the same. And now let's add fault tolerance. I said before, we have replicated. We don't have one controller. Now we have 3 controllers, and they are hearing exactly the same topic. And they are publishing exactly like before this topic. But now we have a difference. This topic is not going to the output device. We reconfigure the middleware and not and not the implementation of the controllers of the building blocks. Okay. In the case before, you remember, the output device was hearing to this topic. Now, instead of the output device, the voter is hearing to this topic. It gets all this data, all this opinion from all controllers, and maybe if we want, it could get the input from the input device too. It takes some decision and it publishes in this new topic. And this new topic will be then attached to the output device. And so we change the configuration in the middleware, and we don't need to change a single line in the building blocks. Okay. I would like to show an example how we do it in satellites. I said before, it's not a special satellite, it's not a special Rhodos, it's just a publish subscriber middleware which is used in satellite by us. Okay. How it works, we have in the satellite many applications and we have a software infrastructure. For the communication between these applications, we might have some private topics. But at the moment, let's take only a look to the software infrastructure of the satellite. It works like this. We have some applications which shall be always in all satellites. We have an anomaly manager, which is like a black box, like a flight recorder, is checking all reports of things which are going wrong, and it can forward this information to the operator so the operator can take some decisions. We have a housekeeper. The housekeeper is collecting important information from all applications of all devices, and it sends a summary of this important information to the operator. So if everything is going okay, the operator can see very fast, everything is like expected. If something is different than expected, then the operator can contact an application and tell, please tell me more. I see something is different than what I am expecting. Then we have a watchdog. In this watchdog is an application who keeps the local computer running. So it collects timing information from all important applications. As long all applications can satisfy its timing requirements, it keeps the hardware of the CPU running. If some important applications have problems with timings, if they are not reacting, if they are maybe off or something like this, then this watchdog will reset the hardware. So, and then this node computer will be started again, and then we have another chance to work correctly. Of course, if we need fault tolerance, we need at least 2 computer nodes which are doing the same. If one is doing a reset, the other one is going to take control and the satellite will not lose control. And then we have a time commands manager. First, we have a commander. The operator may send commands to the satellite, and the commander will distribute the commands to the corresponding applications to be executed where they are expecting. But some commands shall be executed immediately. This is what we call immediate commands, and some commands shall be executed later. For example, when we have no contact to the satellite. And these commands, which shall be executed later, will be stored in the time command manager. It has a list of commands to be executed later, and it's waiting only at the time. When the time for each command arrives, then it takes this command from its list and forwards to the application exactly the same like the commander. Okay, and then we have the downlink manager. That is the communication from the satellite to the ground station. So it gets data from application or from housekeeper or from an anomaly manager, but is in a format for the radio communication is something like the gateway, and then it forwards to the ground station. On the other side, from the ground station to the satellite, we have the upload data manager. That is something like the gateway. It gets data from radio communications and transforms this format from the radio communications to this local format, and then it forwards to the local application. Okay, and this is in principle how every satellite works. I would like to show how we implement this using topics. We have a topic which is called anomaly report. Any application which finds something is wrong, just publish in this anomaly report something is wrong. And this anomaly report had one subscriber, and that is the anomaly manager. And everything anyone says something is wrong, it remembers, okay, something went wrong, and it will report to the operator. The housekeeper is hidden to these anomaly reports too. And it's just taking protocol, remembering when every application reported an application. So it will be an part of the global state information of the satellite. Then we have the I'm alive topic. Every important message will send periodically, I'm alive. My timing is okay. I'm still working. This I'm alive topic has a subscriber, this is the watchdog, and he can see if every application is reporting itself on time. If not, it shall reset the node. The I'm alive can be here by the anomaly manager too. So if it's the topics, the timings are still okay, but they are coming to the limit, then it shall report this as anomaly to the operator. You can say, watch out, we are coming to the limit. Next, we will have a reset. Okay, and then we have the commander. It gets data commands from the earth. We have these topic commands, and it will publish these commands in this topic, which will be subscribed by all applications. So every application might get commands from the earth. Something very similar, like the time command manager, it has a list of commands which shall be executed in the future. When the command is due to be executed, and it publishes it in the same node command. So for the application, it makes no difference if the command which is being executed is coming right now from the ground station, or it's a command which was stored by the time command manager and forwarded later. Okay, and then we have the standard housekeeper and the standard housekeeping request. And this is the housekeeping has a timing and send a request to all applications to say, please tell me what is important now. I'm going to take care of this data as global state information of the satellite. Okay, and then we have two extra telemetry. I said before, as long as the operator can see everything is as expected in this summary of the data from the housekeeper, it's okay. But if the operator would like to see more data from an application, he sends a request to the application using the commands and say, please tell me more. And for this, we have this telemetry history. Extended telemetry or real-time telemetry. And so the application will answer to this command, send me more, using this telemetry real-time. This telemetry real-time will go to the downlink, and from the downlink to the earth. Exactly the same, the housekeeper is publishing its data in this telemetry real-time, which is going to be forwarded to the earth. And maybe there is telemetry which shall be stored, and for this we have the telemetry history. So this data can be sent to the operator later. It's not so important. And for example, when we don't have contact to the satellite is on the other side of the earth, and some applications would like to send some data to the operator, then it will be sent as history. It will be stored in the downlink, and when we have contact to the earth, then we will send this history data to the operator. Okay. And to conclude, I would like to make a comparison of this published subscriber middlewares and the OSI communication layer. And I said before, Rhodos is only a special case of this. This classification is exactly the same, almost exactly the same for all these published subscriber middlewares. Okay, the communication OSI model has 7 layers. We begin with the lower layer, that is the physical layer, and this is how data is transmitted. Here we define which voltage means 1, which voltage means 0, the speed, how many bits per second, bit encoding, how to recognize the begin and end of message of 1 bit, and byte encoding, how to recognize the begin and end of byte. Because if we have a wire or maybe a radio link, we get only bits, and we don't know where a byte begins. And then when we know where a byte begins, this is the next thing, where begins the message. First, in the physical layer, we define how to recognize the beginning of a byte, not only bits, 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 bits. Okay, and then we have the link address and routing. Here, we recognize in the data link the beginning of message, the end of message, and the address where to forward this message, who is the sender and who is the receiver. Then we have the network layer. In the network layer, we have something like a computer address and routing. So we know for each message from where is it coming and how to forward this to the target node. Okay, then we have the transport layer. In the transport layer, we identify the messages in the software. So which ID, which application, and so on. Applications is in the next layer. That is the session, and in the session we identify not only hardware computer, but inside of the computer we can have many different applications, and we can say which message is going to each application. Okay, next is the data representation. And we have a problem, maybe you know this Indianity problem. We have little Indian and big Indian, and this is how to define the sequence of bytes of a message. First the most significant byte, other first the least significant byte. Some computers expect first the most significant byte, and some computers expect first the least significant byte. And that's a really big problem. So this data representation shall know this, which kind of computer we have, and how the messages are encoded. And in case they have a different indianity, we have swap bytes. And here we can have encryptions too in this layer. And the top layer is the application. And these are the the different applications we can have in our computer. Okay, this is the typical OSI layer. If we compare this with the typical publish subscriber middleware, then we see we have really less layers than the typical ISO layer. So we have to find a correspondence. First, we have the physical link, and the physical link is these 3 layers. So including network addresses going down until byte and bit encoding. That is the physical link of a typical publish subscriber middleware. Then we have the gateway. The gateway is forwarding messages from a node to node. And this is the typical network application, a network layer, from which node to which node. And then here we have the applications layer, which says which application shall get the data. And this, of course, that is these topics. In these topics, we know which application shall get the data and which application is producing. And at the top, the user application is the application. So here we have 7 layers, and we compress this 7 layer in these 4 layers in typical publish subscriber middlewares. Okay, and now at the moment, with this, we conclude this topic about distributed operating systems. Thank you very much.